All right, everyone. Thanks for joining me here. This is the fifth of our webinar series for Introduction to Solid Edge. In this webinar, we're going to be looking at solid edge simulation. This is a form of engineering analysis. And what I mean by engineering analysis is if we are designing a product, we can capture all that geometric information in 3D CAD, but the other question is, how will this function in service? When we apply loads to it, what will happen to the structure of this? Is it going to break when it's subjected to service loads? So that type of predicting what's going to happen to a manufactured or designed part or assembly is part of the engineering procedure. And there's been a number of tools developed over the ages to assess that and give designers and engineers a better idea of how to design durable products that will stand up to the field loads that they're meant to. And what we have here in Solid Edge is a form of finite element analysis. And what I mean by finite element analysis, this is a technique that has been developed long ago. It was traditionally done, at first done manually, and then because of its complexity, when computer-aided design was introduced, it's been done through computers. But basically, what we're trying to figure out is the stress and strain of a part. Stress being how the part will react to loads, where failure will occur. So if we can identify that, we've got a much better understanding of how our design is going to function. So finite element analysis is a way of making it mathematically feasible to analyze a component that is made up of complex geometry. And it basically does that by breaking the part into a series of elements. And elements is essentially manageable little chunks. And by analyzing each of those individual chunks on an individual basis and bringing it into the sum of the part, you can get an understanding of how that part functions. So again, you're breaking up a sort of continuous piece of geometry into individual elements, a finite number of them, and then performing the mathematical analysis. So for those of you who have a Getting Started guide, this is section 4 in the guide. For those of you who have a Solid Edge, or all of you will have Solid Edge program, but the electronic version of what we're doing is the simulation exercise down here on the Getting Started with Solid Edge. So let's open up that file, and it's actually going to be under Program Files, Solid Edge, ST4 training. And what we're looking for is an assembly file, so I'm just going to switch down to assembly to trim down my results. And the name of the file is STOADMM. And it is, again, this micrometer that we've been working on over the past few weeks. Now we're going to do analysis on it. Okay. So here's our design all assembled, and let's say as designers we want to know, well, as this piece twists, the micrometer will move in and out. What happens when someone really reefs on this and subjects this frame to a load? I want to know at our maximum predicted operating load how this is going to react. What stresses are going to be present in this frame? So the way we're going to do that is we're going to go into the Simulation tab of the Solid Edge environment. And we're going to create a new study. So by clicking this, I'm going to create a new study. Now, the tool we're using here is Solid Edge Simulation. This is available as part of Solid Edge Premium or as an add-on to Solid Edge. And it is a full suite of finite element analysis. And you can see that we're capable of doing linear static analysis. And what that means is that is stress and strains in a static load. So, here's a fixed load, not changing, and what is the stress and strain going to be. We also have normal modes that we can perform an analysis, and a normal mode is a natural frequency of vibration. If any of you have owned like an old car and you've been driving down the road and you wonder why whenever you hit 80 kilometers an hour it starts to shake violently, that's because you've reached a natural frequency of the car structure, for example, and it begins to resonate. So being able to identify a part or assembly's natural frequencies of vibration is useful, because then you can identify areas where, at certain operating RPMs, you might get resonant frequencies which will amplify the vibration. The last thing we can do in this suite is linear buckling, and that's basically a member in compression, and at what point it becomes unstable. A simple example being, imagine a column. You can load that column up, and before it physically crushes itself, it will probably buckle and break, and it's really a moment of instability that you're trying to identify. So I'm going to start a linear static analysis, and my mesh type is tetrahedral. Now by mesh, we talked about in a finite element analysis, we are breaking geometry up into manageable chunks, and that's your mesh. And a tetrahedral mesh means that those chunks will be tetrahedrons. You see we have some other ways of performing the analysis in Solid Edge. An example would be a surface mesh, and that's if you've got something like a sheet metal piece or something with a uniform thickness, you can further simplify the analysis and create sort of a simple two-dimensional mesh. But we're going to go with the tetrahedral mesh. And the next thing we're going to be asked to do is identify which parts we're including in the analysis. Now Solid Edge can perform an analysis on single parts. Solid Edge simulation rather can perform an analysis on single parts or on whole assemblies. In this case, we're just going to analyze the frame. And the rest of the conditions we will make up with what we call loads. Now before I go any further, I want to bring out my simulation tab, because that will walk us through what we need, the information we need to put in here to perform a study. And that tab is over here on the side. You'll see it here in simulation. If you don't see this tab, just grab any one of these down arrows, and they're kind of all over the place on the interface, and make sure that the simulation tab is turned on. But there it is there, and I'm just going to pin that down. So to complete a study, we need to enter in a bunch of information. We need to accurately describe the operating conditions of this part in order to get an accurate analysis. And the old saying with finite element analysis is that there's no such thing as a wrong analysis. There's only wrong, so there's no wrong questions. Or no wrong answers. There's only wrong questions. And what that basically means is that what you get out of analysis is only as good as the information you provided. So it's important to have an understanding of where your loads are and how this particular part or assembly will be constrained in order to get an accurate answer of how it's going to react. And the tools here in Solid Edge are to make it as easy as possible to apply and change those loads to get an accurate study. So we see down here in our simulation toolbar, and I'll just turn on my magnifying glass so you guys can see, that we've created our first study, static study 1, and you see we can actually have multiple studies. So we can do different types of what-if scenarios for different types of loading scenarios. All working off this geometry. And you see that because I've filled in what geometry I've included in this, it's filled that in for us. So there's the frame 3. And this little pie chart is useful. Once this pie chart is completely filled in green, that means that we have enough information to perform the study. You see that we're still missing quite a bit. And that's our loads, our constraints, our mesh, and connectors. And I'll talk about each of those in turn. So let's talk about loads first. That's pretty straightforward. In Solid Edge, we've got a number of conditions we can apply. The most commonly used might be stress, but we also have pressure, torque, a gravitational load, which is just, what's this thing going to do under its own weight. We even have things like a temperature load, and that would be how will this deform due to thermal expansion or compression. In this case, I'm going to select a force, and I'm going to apply a force on the bearing face of this frame, and that's kind of this face right here. So I'll select that face, and it's going to give me a value, and I actually want that to be 600 micronewtons. So I'll key in 600 and hit tab. Now the direction of my force, represented by this blue arrow, is pulling away from that face, so it's almost like I'd be pulling on it. I actually want to push on it, so I can go up here and flip the direction. And now you see that that arrow is pointed inwards. Notice too that I have a steering wheel, and that's if our force vector can't be described as normal to a face. Maybe it comes off at a weird angle. We can use the steering wheel, and this is again the same familiar tool we've been using to move parts in assemblies and directly edit faces of parts. This can be used to control our direction of our forces or loads in a simulation analysis. So I might use my steering wheel to establish an angle, and now you can see that my force load is at that angle. So this is a very useful tool and a very familiar tool to create an analysis. But that's where I want that load to be coming in, and I'll just hit enter to accept. Now notice over here back in my simulation toolbar, that force has been added to the list. And now our pie is half full. If I want to edit that force, I can just right-click. I can click on the force, and the callout will appear in my 3D space, which I can then click on and make any changes I want. So what else do we need other than force? Well, the next thing we need constraints. Right now I'm pushing on this face, but the program doesn't know, well, are you pushing this along so it's traveling away? How is this thing constrained? So I'm going to apply a constraint, and we have a number of ways we can do this. In this case, a fixed constraint will merely say that, this face or element is not going anywhere. So let's put our constraint here, and just imagine as if this was held fast. This will keep the part stable in 3D space as we apply a load to here. And I'll hit enter. And now that constraint is listed in my toolbar. Notice too that we have things called connectors. If we were analyzing a series of parts in an assembly, we need to tell the program how do these parts act to one another. So an example of a connector would be, if we've got two pieces that are they welded together? Are they rigidly connected like that? Or are they just pressing up against each other such that they can't penetrate the surfaces of one another? These are the types of information you need to supply. Now there's some nice ways to do that in Solid Edge. An auto connect will analyze the assembly and automatically place the constraints for you. You can also get a little bit more hands-on with by manually defining the type of connections. And then we have application-specific connections. A bolted connection is a great one. If you think of this nameplate here, which is bolted to the frame, rather than include those bolts and analyze them, we can use a bolted connection which will simulate the bolt as well as the bearing face of the bolt, the load, the torque load on the bolt, and allow us to kind of simplify that bolt as a connector and really focus our efforts on analyzing what's happening to the parts that's bolting things together. So that's an example of a connector that's very handy, but these you would use if you're analyzing an assembly. Remember that we're just analyzing this single frame element, so we don't need to put any connectors in. The last thing we're going to do is a mesh. And what a mesh does is it breaks down the part into manageable little chunks. And it's doing this mathematically. It's analyzing that geometry, analyzing the coarseness of the mesh that we've specified, and it's going to break it into tetrahedrons. And you'll see what it actually looks like. What you're going to find in finite element analysis is that we are always trying to balance accuracy with expediency. Mathematically analyzing all of these mesh elements requires some degree of computational power. And we need to focus that computational power on the areas that we're concerned with and kind of trim away what we don't need. So if I'm only concerned with this frame and how it reacts, I don't need to analyze the other parts in this assembly. We're only focusing on the frame. Similarly, I can decide how fine I want that mesh. Generally speaking, though not always, a finer mesh will result in a more accurate analysis, but it will also be more time-consuming for your computer to chug through that number crunching. So there's my mesh. I can dial up that coarseness, or I can further refine my mesh, and we'll look at that in a minute. And the last thing I'm going to do is solve this. So you see that my pie is 3/4 full. The last thing I need is to solve it. So it's going to take all that information I've put in, and it's going to analyze this, the elements, and show me how this is going to react under load. So again, depending on the complexity of the problem, the amount of geometry, the fineness of your mesh, it will take different amounts of time to analyze this. So, for the most expedient process, you want to make sure that you're doing this efficiently. This tool, again, is for an engineer or designer who wants to kind of get an accurate idea of how it will perform under load and maybe try some things out. Make a change here, make a change there, do the analysis again, and see how that affects the performance. So now we've got a display of the part under load. And what are we looking at here? Well, you notice that we've kind of got two things going on. The first is that the model has deformed. It's actually an exaggerated deformation to kind of show us where the displacement is occurring as this bends under load. The next thing we see is the color bands, and that identifies the areas of stress. Obviously, if you look on this bar on the side, as we move up this color to red, that is the higher stress concentration. So I'll just zoom in here, and you see our maximum is 175 kilopascals. We're analyzing this in metric, so we're looking at our readout in kilopascals. That is our maximum stress, and you can see it's occurring right here where the arm meets the rest of the frame here. That's where our area of maximum stress. Now there's a number of ways we can analyze this. We can change how this is displayed. One thing I like over here in the color bar tab, and again we're in the results environment, is to turn on that maximum stress marker. That's going to put a little call out to show us where that maximum stress is occurring. Sometimes it's not obvious where that's happening. The other thing we can do is we can probe other areas to figure out what the stress is. So if I want to know what the stress is maybe on this other side, I can pick an intersection of elements, and it'll show me that at that point I have 120 kilopascals of stress, and it will drop these probing marks in a table which we can then save to Excel. So we can get a lot of information from this. We can also animate this to show, kind of see how that deformation occurs as we load that up. And notice that the color bands update as that goes. And of course we can save this animation out for later use. So let's say we've looked at this now and we said, all right, well now we have an idea of a stress concentration here. We know where our highest stress is occurring. We think it's somewhere around 175 kilopascals. And again, that's based on the information we've provided it and the level of the granularity of the mesh that we've put in. So I'm going to close the results, and our simulation you see is still saved on the side, and let's make some modifications to the model. Let's see if we can get that stress to come down. So the first thing I'm going to do is I'm going to go back to my Home tab, and under Select I'm going to switch to Face Priority. And for those of you who tuned into the earlier webinars, you'll know that this allows us to select the face of a part, and then it will call up all the dimensions that drive that part. And I can either click my arrow to begin to dynamically change the position of that face, and I can kind of eyeball that or key in a precision value. Alternately, I can select some of the dimensions that are already here. So for example, this dimension is the base of that frame to the center bore of this area here. And I can increase that to something like 52 millimeters just by clicking on it. So I've increased the thickness of my frame to try to alleviate some of that stress. The other thing I may want to do is going back into that simulation, and you see I'm still in my static study 1. I can edit any one of these. I may want to add some mesh refinement, and what this means is that I can choose an area where I want a bit of a finer mesh. I know that my stress is occurring kind of in this area here, so I'm going to select that face and say that I want a mesh size of 1.5 millimeters. That means that my tetrahedrons will now be 1.5 millimeters in width, whereas before they were about 2 millimeters. So I'll hit Accept. Notice that over here in the toolbar, that mesh refinement for that particular surface has been added to our toolbar. Notice too, and I'll just turn on my magnifying glass again, notice too that we get these little exclamation marks, and our pie, part of our pie is yellow. What this means is that with the changes we made to the geometry, our overall mesh is out of date, as are our results. So we'll need to recalculate those before we can view these results again. So I'll hit Mesh, and I'll recalculate the mesh. And now this might take a little bit more time because we've said we want a finer mesh in this area here. We've also increased the thickness of the frame in an effort to alleviate some of that stress. So you'll see that there the mesh is updated, and you see we got a finer mesh in this area here. So we're hoping for a little less granularity, really get some answers there. So that looks good. I'm going to go right away and solve that. And we'll see if we've alleviated any of the stress. Remember that last time it was 175 kilopascals. Also note too that we didn't have to redefine our study. We didn't have to redefine that load or the constraints. Solid Edge will only prompt you to change what is out of date. And this allows you to kind of go back and make those changes, do those what we call stink tests, where you want to say, well, what happens if I increase this? What happens if I increase that? And this is for a designer to kind of iteratively design something to a satisfactory level where you're confident in terms of how it will perform in the field. All right, so it's recalculated our stress levels, but notice that we actually haven't changed anything, and that's because if you think about it, increasing the thickness of this isn't really going to alleviate the stress that's happening there. So back to the drawing board. I'm going to close my results, and this time instead I'm going to increase the thickness of this arm because that may do better. So this time I'll click on that face and I'll use my steering wheel and I'll just kind of pull that out and maybe key in, maybe I want that to be 3 millimeters thicker. So it'll go and do that. My mesh is now out of date, so I want to remesh and then solve that again. So this is an example of how a very intuitive finite element analysis tool allows you to set up an accurate analysis. And synchronous technology gives you the ability to rapidly perform these design changes so that you can get closer and closer to a finished design. Again, this is not a substitute for a dedicated analyst who's an absolute expert in this, but as the designer, you can at least get yourself closer to a final iteration and not have to rely on a third party to do this. So my analysis is completed, and you can see that if I turn on my magnifying glass, we've brought that maximum stress down to 112 kPa. And we can double check that by going into our color bar tab and turning on that maximum marker. And there it is. The maximum stress is still occurring in that area, but we've brought it down quite significantly. So I'm pretty happy with that. Maybe this time what I want to do is document these studies. Oops, I just closed out of my results. I can go back into that by clicking on results. It doesn't have to reprocess because I haven't changed any of the geometry. But what I'm going to do is I'm going to create a report, and that's going to document sort of where we've been and the output of this analysis. So you can hit Create Report. We can type in some stuff. This is our new design for the micrometer frame, and then we can say increasing our conclusion. We'll say increasing arm thickness created satisfactory results. And you see that we can create this report in a web format or different Microsoft Word formats. I'm going to go with Word 2007, and I'll just create that report. So right here in my 3D analysis, or in my 3D environment, Solid Edge will save this simulation study, a static study 1. I can rename this anything I want, but it will save that study so I can keep revisiting it as my design evolves. But additionally, it's documented automatically a simulation report for this particular scenario. And it will record things like our material properties and the loads that we put in, the type of loads. So we've got a way of rapidly documenting the results of these analyses to keep track of sort of where our design, our iterative design, has taken us. And this is a very handy thing. So that concludes what I wanted to show relative to this study. Remember that these are recorded, so you can come back here and use this as a reference as you work your way through the self-paced training, through the Getting Started guide, or through the Getting Started tutorials. I'm going to stop recording and open it up to questions now.